Okay, so what were we talking about?
Forever.
It's been forever, right? Did you guys enjoy the extra long break? Another half week? This is like a third half week this semester. First the strike and then the flood and now President's Day.
Okay.
So I don't have a homework for you this week because I don't think, relax, okay, relax. Because I don't think there's enough content to go over. But I do want to make sure the folks of you who have turned in homework from last week and gotten feedback on it, you're in the right ballpark, right? You're definitely using probabilities properly. But not always thinking about the full sample space. So, and we can talk about these separately afterwards. So the thing that I really want you to consider is, have I enumerated all the possibilities? Is there different ways to consider how it's written? So I saw some really good pictures. For example, like a flow chart of all the potential outcomes is a great way of stacking how you do all of the potential outcomes. And then you can assume, okay, if it goes down this path, it has this probability, goes down this path, it has a different probability, right? Okay, anyone get 100%?
No, right numbers on it.
No, but no one got 100%, that's okay. All of the problems, right? Were those too difficult?
I think they were fair.
They're fair, right? Okay. We were talking about moments of the distribution. And today I wanted to talk about using something like the variance and what it means in a distribution. And then we'll talk about some common distributions. Because of all these half weeks, right, it's kind of cutting into the amount of time that I wish I had put aside for the entire, like, if I could just do probabilities and statistics for an entire semester, I think we'd be well on track. But we're kind of running into the time period that I wanted to reserve for general relativity. So there is slack at the end of the semester. I always build in like an extra week of content. But we'll try and move past the probability part. You've learned most of how to construct probabilities. You've learned Bayes' theorem. I'll show you some simple probability distributions and then some complex ones. And we'll apply moments to them so that you can use them on data. And then we'll talk about statistics. So this might be one of the last days we talk about probability in the traditional sense. And we'll move on to the broader field of how to use it when we interpret data. Good. Questions, comments, concerns? All right. What was the variance? Do a really quick recap for the brain. Okay, good. There's the word expectation value. What's an expectation value? No trick here.
This is the average.
Nope, not the average.
Oh, highest probability of occurring.
So remember that means and averages have specific definitions.
Yeah.
An expectation value is the expected value. So if I ask for something like the expectation value of X, what does that mean?
Add all up with their weights.
You add them all up with their weights. And if their weights are all equal, that would be equivalent to an average, right? So what is the expected value of X? It's the mean. Okay, so what is the expected value of X squared? Is there a simple answer for that? An easy interpretation? What's that? No, not really. Okay, so we're going to interpret it in a few seconds. So I gave you this derivation that had to do with, let's see, where did I write it? Okay, we were talking about the moments. We said something along the variance V of a distribution. Let's say some distribution of X, right, is the expectation value of a quantity X minus mu. Right. Remember that? Yeah. Yes or no? Okay. There. Good, and how did we write this?
That's. Square is big X. Plus leaf square.
Good, what's this?
Mu.
Good, so what's this?
It's EX squared plus U squared.
Nope.
Minus U square.
Okay. So we've defined something called the variance. Okay, and this is really, it's a second moment of the distribution, so when we say the moment, I mean what power of X are we having? And this is something that we call a central moment. Reason that it's central, is right here. So I'm not talking about all of the distribution, talking about finding the central and then taking the moment about that. Does that make sense? The word moments make sense to you? What a moment is? Moment is simply taking whether it's a functional distribution, whether it's a probability distribution, and then applying a operator to it here in the context of X, or some power of X. So when we think of these in mathematical terms, these are sort of abstract concepts, because what you're doing here when you're taking a moment, you are attempting to derive information from the distribution itself. And each one of the pieces of the distribution is going to tell you something different. So the first one told you something that we could kind of see by eye, which was the mean, right? Okay, so let's remember that we have to go back to the data to really understand these. So here's our data. And what was the mean for 2 dice rolls?
Like.
Well, you all calculated it as soon as you left the class, right? Is that correct? I got 7 right. That was weird. Huh, crazy. Is it right?
Yeah. So,
You're saying it really confidently. Did you calculate it? No, so calculate it. Oh, so let's remember, how do we calculate the mean?
oh, it's the. Yeah.
And what's the sum that I write here? What?
1 times 112.
Let's write the sum first, so I can write it in a generalized sense.
Yeah, so it
For a discrete distribution like dice rolling,
is, well, 1/6 times the value of the base.
and right, x
Yeah,
times f of x.
okay.
And this is the generalized way that we think about discrete distributions. Now you can go through and you can say, okay, there's one way to make what? 2. Good. And since I know that it's probably going to be symmetric, I could just add them on the other side. So there's probably also one way to make. Good. All right, continue. Yeah. No, not 7? What'd you get?
259.
252. Okay, so was it really 1 that I was supposed to multiply by there? What? 1/6? How many dice are there? That's not how we do samples. How did we construct this? Go back, memories, folks. 1/36, because it's 6 times 6. There's only one probability out of 36, which I can get 2.
Divided by 36.
Ah, okay, good. So remember that this f of x is not just the number of ways that you can get it, but it's the probability that you get it. Okay, okay. And then you get what for 2 dice? You claim 7. Anyone else get a different number? Good, that's correct. All right, that's an 8. What's the variance of this distribution? What does it mean? You the whole class has it.
For the e of x squared, would you plug in the x squared to the f of x too? To the weights part?
Yeah, so you could do this one of 2 ways. You can either directly calculate this to get this, or you can directly calculate this and then subtract that.
Yeah.
Either one is equivalent. And in both cases, you're really gonna do it exactly as it's written here. So the expectation value simply says E of anything, right? Put whatever you want in there, equal to, in this case, the sum of that thing times f of x. Right?
So the f of x does not get anything plugged in ever.
Well, it'll be for whatever that x was.
Well, isn't it obviously a question of probability? Like that's how.
Yeah. So let's take the first one, and we'll do the first one together. Let's say you want to calculate this. Okay. So E of x squared, just like we did over there, right, is going to be the sum of x squared times f.
Not f of x squared.
Just f of x.
F of x.
Yeah, good question. So the first one is
It would just be.
2. So the first number is 2, good, and then the first number here is 4 times.
36. I was trying to figure out how to do like 1/36 squared. Oh, you just.
No, just the function itself. In every time that we take the moment, it's only one, it's just the probability distribution itself. And I think I wrote that in the notes, but just write it on the board really quick. So here's how we write any. So for any moment, right like this, mu k. And I'm putting the k down here to indicate which moment it is. So it'd be the expectation value of x to the power k, which is defined as sigma x to the k f of x, or the integral x to the k. Yes. C'est bon? You haven't memorized your squares of the 12? Come on, folks. Oh, well, those are, computers can do those. But these ones are cool when you work them out. Wolfram Alpha, yeah, that's true. All right, what's the number?
That one's 54.83.
54. That we said? 54.833, so you did all the numbers? You did all the numbers? Sure about that? Well, let's look at the distribution itself. It goes between 2 and 12. Now, you don't yet have a real understanding of what the variance is or of what the expectation value of x squared is. But even if I look at all the numbers, you know, the difference here is 10 between the whole range. 10 squared would be 100. So that's like half the range that you're thinking. Number 54 is very big, right? Look at the mean. The mean itself is 7.
Yeah.
Okay, so if the variance is,
So you want to vary by like 5.
well, I don't know, you tell me.
Well, I just got the x squared up subtracting that. So it should be.
Oh, you didn't subtract this.
Yeah,
Okay,
you're
sorry.
right, just the x.
No, you're right. Okay, so what's the expectation value of x squared?
54.8.
Okay, good. 54.8. Now
But when I
before
subtract
we
it,
do
it's
this.
about 5.8.
Ah, there we go. Okay. So the variance here, when you subtract off the mean squared, which is 49. Right? So the variance here, V.
We have here x is mu, and it equals 7, so subtracting 7 squared. Oh.
Okay, so this part here was this part here. All right, I know that my notes here are fucked. And then this one here, that over there, and this one here is that over there. Okay, and the variance was?
5.8.
What does it mean? Come on, just maybe do it. Do. That's right. Yeah, so this is how we tend to think in terms of a distribution. What is its width? Variance is going to tell you something about its width.
That's a little bit wider.
Right, well, actually, the interesting part here is the variance, if you look, what units does the variance have?
For probability, what is that?
Let me say this a different way. If we thought about it as a width, we thought about the numbers as, you know, this is some number of feet. Yeah, is it length? So if the mean was, you know, this middle position, what would the variance be? Look at the power of x here. Right? The variance of the two dice in here is x squared and mu squared. So all the lengths or all the probabilities are multiplied by themselves. So if they had units, they don't in a certain sense, but if they had units, you'd be thinking about them in the context of meters squared. So if you wanted to describe, say, okay, this is say maybe the central position of something that's walking around, right? So it mostly ends up at 7 meters. I didn't actually line it properly. Imagine that's over the 7. Okay. And then you say, well, how far does it deviate? The variance here, what?
Area?
Yeah, the variance here is an area, so I have to undo that. So I'm going to say something, I'm going to call it sigma. I'm going to say sigma squared is equal to the variance. And sigma, we're going to define as the width of the distribution. What's that?
Why is it of the distribution and not of the, oh.
This is the variance of the distribution, and this is the width of the distribution. It's a way of thinking about it. These words are more easily seen when we have a continuous distribution. So you'll see everyone's favorite, which is the normal or the Gaussian distribution. And you'll see sigma is that same sigma that we're talking about before. So in a Gaussian distribution, if you're at the center, at the mean, you move one sigma away on either side, you have about 68% of the entire distribution. All of the probability that would fall within, one sigma of either side is sort of captured. And so you may hear statements like, that's a 3 sigma result. So what does that mean in this context?
Maybe it's outside the distribution.
Good question. Out of this distribution for sure. Let's first figure out what this one's sigma is. For 5.8. 0.5. Okay. So this is the mean. And I drew this perfectly so that the 7 is right there. Good. And so this is mean. So this is a mu. Okay. And now I'm going to go off in each direction. And I'm going to go off by 2.4. So that takes me to about where? Very good. 9.4 is right here. This would be sigma plus mu. And how do I go this way?
4.6.
Correct. Okay, this is sigma minus mu, or sorry, mu minus sigma.
No, that's not how wide it is.
But that's not how wide it is. Good. This is a measure of the width. This is not saying it is the total width. So you've heard things like 3 sigma. And this is telling you, when I'm telling you that it's 3 sigma for a Gaussian distribution, I get almost 99% of the distribution. But there's still stuff outside of it. There's still 5 sigma results or 10 sigma results that might live outside of the distribution. When you have a continuous distribution, those numbers can go off to infinity. And you may never get the entire distribution unless you integrate from minus infinity to infinity.
So what's the point of sigma then if it's not even right?
Well, so when we say right, what do we mean by it? We are not talking about here calculating something that is true and able to tell us like about the world. What we're doing is we're attempting to take something and give it a quantifiable metric that I can compare to other things similar to it. So if, for example, I wanted to compare 2 discrete probability distributions, I might ask which one of them is wider. Now, does it make more sense for me to give you all of the numbers which they range? Or does it make more sense for me to give you something that I can derive from the distribution itself that will change based on how these values are distributed? Okay, because let's imagine 2 scenarios. Okay, I have here, 2 die, great. And I made this distribution. But let's say I play Dungeons and Dragons or something like that, and I have a D12 or a D2 through 12 with no 1 on it. Okay, if I roll that die and there's only one outcome for each number, what does the distribution look like? Yeah, no worries. Okay, so these are the Dungeons and Dragons immediately up. Okay, so here's the 2 dice here, and this has a curved distribution, has a shape to it.
Yeah.
But I said earlier that 1 die has what kind of distribution? No, it's tricky, right? It becomes trickier every time I add a die. Well, this one here, yeah, so in the example I just gave, it was by 12, but if I just use a normal die, it would be by 6, right?
Yeah.
And in both cases, you're only dividing by that number. So the distribution becomes
Line.
a line, it's flat. Okay, so now your question about width is really important. So which one is wider? You see the question yet?
Isn't it the
Okay.
facilities both that be whites?
So look at this. This is the distribution. This is the distribution of the D12, or the weird D12 that doesn't have a 1.
Yeah.
Okay, equal probability everywhere. So which distribution is wider?
Has to be the default.
Yeah, it must be, right? The range is the same. They cover the same numbers. Right? But you're just as likely to get a 2 as a 12. Right? So this is a measurement of how sharply peaked is the distribution. You see?
Mhm.
Okay, so when I say width, I don't really mean width. I mean like, how do you look? You know? Does that make sense? Okay. All right,
So it's not in like, like this,
not really. Yeah.
it's more like stretching.
Yeah, so each one of these distributions will give you something new. So the first one, we called the mean. Right? And that basically told you roughly where the top was. Now, we saw that wasn't exactly right because there's the median and the mode, and they all kind of sit different with regards. But then you could take the square of the distribution, the second central moment of the distribution, and that tells you roughly the width. And you say, well, what if the third? I'm not gonna make you do it here. What does the third tell you? We have even distributions so far, but the third central moment will tell you about the skew. And that will tell you how much more stuff is to the left versus the right. So if the distribution looked like that, right, it would have a positive skew. If the distribution looked like that, it would have a negative skew. And if it looked like that, zeros. You see, and so each one of this is telling us something more, and then you take the fourth moment and you learn about something really cool called kurtosis. But we're not going to go into that. Does that make sense? Okay. You upset? Upset? Just one. What? Not about life, just about these distributions.
Like.
She said like.
Light work. Okay, good. So let's learn the distributions. Can I delete this all?
Yeah. But there's equal probability to get a low, like the low lows versus the high low. Then you add with the high.
Good.
He's having trouble like understanding like the whole like shallow low wide and peak for variance with the D12 example versus the 2D6.
We can do it.
No, I did the math. Why?
It's fine. Yeah, well, it's like anytime you have a flat distribution, it necessarily forces a wider
So
distribution.
the higher the peak, the
So we don't want to say words like higher. Right, because the picture that I drew isn't correct, right? It's not 1 all the way across. That was the number of times. So we always have to divide by the sample space at the end. So comparing two relative heights may not matter because that's just talking about the frequency, which is just the number between 0 and 1. But the width, the hand motion you made is correct, right? Is it like this or is it like this, right? And so you have two examples, right? You have the two extremes, one of which would be a flat distribution or a uniform distribution. What would the other extreme be? Yeah, what's that called? Super steep distribution. It has a D in Greek. The delta function. Yeah, so the delta function, very good. The delta Dirac function is a probability distribution, which says I am nowhere except for X.
Yeah.
Right? Sure. Whatever, bro. You're fucking teaching. Okay, so here's two distributions, right? So here's a function. That's a uniform distribution, right? And this would be the same everywhere. Same for all values of X. Or, actually, we should use a different letter. Right? Right? Okay, and you've seen that before.
Yes.
I made you do that before. Too much probably. No, okay, good. Okay, so let's, I don't know if I wanna give you this example. It's a good example. Okay, now I wanna give you this example.
We should get the.
Okay, so, we're talking about a lot of distributions that you're like, well, I'll never see that. But of course, many of you play fantasy baseball, just like me, right?
Yeah.
You play D&D? Okay, that's important, then you gotta know the distribution of roles.
Yeah.
Okay. So, if you play fantasy baseball, at the beginning, you have to draft players. Okay, so you have to select players at different positions, and they all have different projected points. So let's say you're a real fucking nerd. Okay, I don't know who this would be, but imagine one of you was a nerd and you built a spreadsheet. And you listed all of the players and how many points they were projected to get at each position. I'm not gonna comment on what I may or may not do now. Okay, so let's say you have a really big table and it has all 9 positions in the infield plus the starting pitcher and the relief pitchers. Okay, and you have to make a decision, right? Because you gotta construct your team. So what if I give you 3 different numbers, okay? So I'm gonna give you the mean of the distribution. I'm gonna give you the width of the distribution. And I'm gonna give you the skew of the distribution. So this one is gonna tell us the mean of the top 30 players at each position. This will tell you the width. And this will tell you the skew. Well, I'm not gonna write that again. Okay, how do you use this information, these 3 pieces of information, to make your next pick as to which position you want to use?
What if you want to get anyone within like plus or minus sigma mu? Or sigma plus or minus mu, that is what it should say, because those are like the players that will like on average be like the best.
Okay, so let's remember, there's multiple columns. You can select from all of these players. And they're constructed, all 3 of these numbers, number 1, 2, number 3. For this column, number 1, number 2, number 3. For this column, so on and so forth. And this is maybe the catcher, first baseman, second baseman. So the question I'm asking you is, how do you use these numbers, which you can construct for any distribution of numbers, to inform these decision-making choices?
We could do it like by position, and each position we find the width and.
Yeah, that's what I've done, or that's what someone might have done it in this fictional example that doesn't. Yeah, okay, well, and the internet.
Just John.
Just John, Trinity. Okay, so how do I, what I'm trying to do right now is I'm trying to show you that there are real world applications. Any set of numbers can be constructed with these in mind. And let's say you don't decide to go into science, or in grad school, you get poached by Google. They will want to know whether you understand how distributions work. Because what they'll do is they'll make decisions in business based on numbers. Shocking, right? Okay, so can you back up these numbers and can you interpret them meaningfully? So what does the mean tell you for each of these columns?
So it's like,
Who's most likely to make points? Yeah, who's most likely to be good? So you might start over here and say, oh, the outfielders, they have the highest mean. Good. So would you immediately choose an outfielder? No, why not?
wait, that's just the best, not best of the out. Like,
Well, you can only pick one person at a time, and then everyone else gets to pick, and the distribution, right? All of the relative people is going, it's a draft. Never done a draft before? Never heard of a draft?
I've heard.
I've,
Never heard of a draft?
I've been like,
Y'all really are
elementary
physicists.
school.
Exactly, that's the same thing we're doing, except it's a fictional world.
Yeah, it's literally that.
Pick one player at a time for each thing.
And
So
then
you
the
have to
other
pick
people are
one
gonna
for
pick the
one.
best as well.
Yeah, so you're competing against other people, right? And so you only get to pick one person total, and then the next person picks a person, and they can pick from anyone.
Yeah, I think for me, I would choose the best, the person that has the highest mean.
Okay, that seems right first, right? So that draws your eye to the outfielder column. Now, is this right?
You're applying.
You also got.
I'm implying it's not because I told you about two new numbers. So what do these mean and how do we use them? We can see the width of the distribution, right? So let's ask a different question here. If the width of the distribution is really, really wide, let's say this one, the mean is big. Oops, that's supposed to be the mean. And this is a very large width. What does that mean?
Basically, every player within that range is equally skilled.
Exactly. Right?
You could still traveling like to math is like the same possibility.
Yeah, like having similar points, right?
And if
Yeah.
it's
So-
skewed, you wanna go left or right?
What's that?
And if it's skewed, you wanna go more left or more right?
Yeah, we'll get to that one in 1 second. But in this particular circumstance, if I saw that the mean was high, but also the standard deviation was very high. Yeah, it doesn't really matter if I pick someone up here or down here, because they'll probably be very comparable. Even though their mean is high. So what would I kind of want to look for?
Like, parts of the players have different. Not points, but what is that called, the width?
Yeah, the width is big or small.
Instead,
Well, they won't. you
Oh,
won't-
so,
they'll have the-
no, I interrupted you, I'm sorry. But,
So let's have a look at what this looks like in practice. Okay, here's the list. And I'm gonna show you the point values, ready? Okay, so these are high point values at the top of the list. And these are low point values. Okay,
or right.
yeah, well, you wanna pick, you obviously want to pick from up here, good. Okay, but if I think about this, right, these things have meaning. So this mean, right, is saying, I don't get the negative values. I'm only picking from the highest values down. So they're all gonna be positive values. So the mean is actually gonna end up somewhere over here. Right? And the width is like how far do you go out, like that.
So
These two are describing different functions here.
so the lower the width on that scale, what happens? It's if it's low.
Yeah, good question. So let's draw another one with a low width. You see, this width is smaller. In the same distribution. Well, no, the same type of ranking here. Let's say the mean is the same here. But the width is much smaller. Who should you take first?
you should take the one at the very top. Because with the lower variance, that means that there's a highest skill, discrepancy between the players.
Right, large skill discrepancy here. Because the distribution of the numbers here is much smaller, the width is much smaller. There's only a few really high value targets here. Whereas here there are many high value targets. So you can ignore this one until this is exhausted, right? And then the mean comes down and then you have to switch over.
So it's
I
more
would
like,
like to get tracks if it goes down though, like one really good player.
Yeah, it's a bad example. I mean, it's, you know, it's an extreme example, but this is how data does work.
it's showing a really small variance.
Very small variance, right?
That's okay.
This one's wide.
What
But
is
the-
variance in baseball, like the field or the points or?
Well, that's okay, that's a much more complicated question. We're gonna sabermetrics. If you actually wanna know why they vary, but let's just assume the numbers are what they are. Okay, then the skew tells us what?
So I believe skew, it basically just says like. How much it means like to the left or right of, compared to a normal Gaussian curve.
Well, we don't know anything about a Gaussian curve yet, but yeah.
Oh, if it's to the right, it's their overall.
Yeah, sorry, yeah, you are looking at them that way. Because they're, each one of them is a column. Oh, no, sorry, it's not this way, it's this way, like the columns are.
Yeah, that's side.
Sorry, I should have said that. So the values are in this direction, and this is number 1, number 30, number 500. Right, because each of the players are in a column. Okay, sorry, I didn't clarify that. And then their point values are up here. Points. Okay.
So it's really like,
The skew is like how shifted, how much is like clumped to one side or the other.
Right. It's another way of determining, okay, so this is the mean, which is like shifted away from the top.
Right.
And so the skew would be how close is the mean towards the actual peak? Are there equal amounts on both sides? Is there much more on one side than the other? Does that make sense?
I mean, what we have.
Well, the peak is just the first person, right? So if you rank them all in how many points they get, it's the first person. But the mean is not gonna be the first person, it's gonna shift way down because it's weighted by all the people at the bottom. Okay. Okay, does that give you a more intuitive sense or did that not help at all? It helped you move your head, good, yeah, I'm gonna show you many distributions in many different directions. All right, so let's talk about the first distribution that we're gonna talk about today, which is the simplest, but potentially the most widely used. Okay, it's called the binomial distribution. What? You ready for baseball? Spring training starts on Saturday.
Oh yeah, make a fence, even put $100 down.
If any of you wants to learn sabermetrics, there's tons of money in it. But you have to like data, like love data. So you make models and then you make betting models, and then you try to beat Vegas. Vegas gets really mad. Accountants?
Yeah, that's all they do, like.
I don't know, that's embezzling.
Never mind.
Okay, so let's talk about the first one. This is the binomial distribution. You ever heard of this before?
Yes.
What is it? Wanna know? Sarah?
Number distribution,
Two what?
number distribution.
Two number distribution, good. So let's break it down. Bi means two, nomial means number. Good, that's 90% of it. So let's just add some context. I don't know if it is, that's why we're not doing grades. Okay, so what does binomial mean in this context?
I was just thinking of X squared, but
Okay. So the distribution, this is a discrete distribution. With two outcomes. You can call them A and B. Or you can call B not A. I don't care. Does that make sense? But there can't be A, B, and not AB. Is that fair? Okay. Kind of or not kind of?
It keeps on looking all the time.
Okay, so let's give you, no, first let's do examples of it. What is a binomial distribution that could be represented with die? Rolling a one or not one? Okay, something can happen or not happen. What's another one?
I thought you meant like not a die that has so many like numbers on it, just one thing, like a quarter.
Yeah, so that would be the simplest, right? Heads and tails would be a binomial distribution. But it's the stupidest one. So we'll want to make sure that whatever we look at here, at least becomes heads or tails at the end. Because we can understand the heads or tails, like that's the first thing that anyone ever learns in heads or tails, right?
But you can still.
You teach a
do
baby
that.
that. What?
It still works with like die.
Does it?
Even though it has 6 sides.
Well, that's the question. What other things can I construct this? We said one and not one.
Less than 3 or greater.
Less than three, greater than three. Mine, I had one in my head and I'm surprised I already said it.
Well, like the solid die.
Even and odd, right? That's good. Okay, so how do you calculate it? Well, let's say you have some probability of A. We'll call that P. What is the probability of B?
1 minus 2.
Very good. All right, now we're in business. Okay? And let's perform n trials. So let's do something n times. Okay? And we want to know x is the number of times, oops. We get A. Okay, so let's fill this all in. Does anyone actually have one? I always forget to bring my cold one. So let's do the number of times we get heads. Well, alright. So let's calculate the probability that in n trials, we will obtain x successes.
Wait,
Okay. Let's calculate the probability that in n trials, we will have x successes. So I am a headsman all the way. I only want heads. I'm going, don't run the trials yet. You have to put money on it first. Okay, so I have a heads here. And I'm gonna flip it 6 times. I want to get 3 heads. Am I or am I not going to get 3 heads?
I think, yeah. If it's 50% chance. And you're giving them 50% of the time.
Anyone online? Wanna bet money?
yeah, we got like fashion.
That's right here.
John.
Throwing real money in. Boost your chances.
Yeah, I'll bet $20 that you will get 3 heads.
$20, 3 heads.
I'll always do that.
Sorry.
Anyone else?
I don't know what the distribution is. 20, there's not 3 heads in a row.
Is it in a row or?
No, just 3 out of 6.
Oh, wait, take my money out.
No, that makes it more interesting.
Yeah, but I don't wanna do that.
Okay, well, what do you want? Nothing?
Let me see everyone else spends, not just mine.
That's not how we're doing this game.
Yeah,
That's not.
Like this week and next week?
What's that?
How much longer?
Are we ready?
Oh, yeah, the stakes are higher.
I'll do 10 on, there's gonna be.
10 on there's gonna be free.
Yeah, 10 on the.
I'm gonna look for how much we do.
Make mine 50.
Oh, God.
You don't want to.
Calm down. Okay, you put 20 on the lines, 32.
On Bria? 10?
Fine. See how- yeah, that's-
Better, it's on canvas.
On canvas, go to that.
Sure, let's do 20. I haven't bet like a good amount yet.
Better.
For an old.
Alright, Rita, you in? Yeah. Don't be calculating probabilities over there. You're not in?
I just lost my mind.
Anyone else?
I'll do 50, there's not three heads.
50, there's not.
I'm sure it's wrong, but
All right.
that's why I'm doing it, council.
Okay, so we're saying something like n equals 6 and x equals 3. Ready?
Why would you throw it like that?
Tails.
You changed the outcome.
This is chaos.
Heads.
Every head is a loss of people.
Tails.
Oh my goodness, God.
Heads.
No.
All right, ready?
Yeah,
Very good.
Ready? Ready?
Are you?
Tails.
What
What do you think? What do you think? Anyone want to change their bet?
No,
Oh,
I'm sticking, I'm sticking.
We can still change?
Yeah, if you want to right now.
It's.
You just go.
Does this new information help you?
No.
No.
No, it does not help you, right? Okay, ready? But it feels exciting, doesn't it?
Like I should have.
Yes.
Oh. Oh, no.
This is chance? Is that what you said? That's correct. It is chance. That is the point of this game. All right.
Don't take a great job, just tell you.
I'm actually 100.
Good job.
Okay. So what was the probability reading?
0.3 for what? Of 3 heads in front? Oh,
How's that possible?
That's 103.
How's that possible, Reed?
yeah.
Oh, okay, so he would have to be equal to 0.5, because we're dealing with a point, right? So,
Well, did you calculate it? Yeah.
Yeah, so how did you do it?
Yeah, so I did, they do the example in the book. I read the book.
Nice.
Coming to class prepared. Doesn't even lose money. Okay.
And so I used the equation that they did.
Okay.
Which was the combinations,
Mhm.
C times, 1/2 to the power of n.
Okay. That's getting way ahead of ourselves. There's an easier way to do it, right?
Probably.
Okay, so let's think about it. Okay? The trials are assumed to be independent. The probability of each trial is 1/2, so it's equal probabilities for each. There are 6 trials. Right? So I have a piece that goes like P of X times, let's say, Q, where we're gonna call Q is equal to 1 minus P. This just flips around, looks like the opposite. And this would be what? N minus X. That's the generalized way of doing it. And then, as you mentioned, there are combinations. There's many, many different ways for me to have flipped 3 heads or not 3 heads. Okay, so how do I do the combinations for that? What?
Of course you did.
Yeah, that's the point. This is the probability distribution, okay? So the total number of permutations of n objects of which x are identical.
Like the number factorial divided by the events taking place factorial times the n divided by blah, 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 get that equation. And then n minus x or x minus n.
yeah, no,
Very good.
Oh, yeah. No, this is.
Oh, yeah, everyone remembers this now. Yeah, this is the binomial coefficient. This is the
Yeah.
binomial.
When we did like the whole table of. This is my project, so, okay, we'll turn it right now.
Okay, so that's why this is called the binomial distribution, the binomial coefficient. N choose x. Okay, that's what you say, literally, n choose x when you see this, n choose x. Okay, yeah,
What is the binomial coefficient exactly? Like, I know it's like a number.
it's that. This is the binomial coefficient. This is the number of permutations of which x can be drawn from n. Number of permutations, right? And we talked about this when we talked about ways of counting. So what is it for this example? The n is very good. And what's that? 50? You're just guess numbers here. Okay, 6 factorial over
1/3, maybe.
That's great.
what is it? What? That's what I did. That'll be right. Okay, so n minus 3, so 6 minus 3 is 3, so I got that right. This one was 3, got that right. This was 6. Okay, so these ones get rid of everything above below 3, so it's 6 times 5 times 4. Divided by 3 times 2, like sort of the 6.
I hate how you do that.
No,
Just put it every time.
Just what?
Say
What?
what? Every time.
You didn't like my math? I'll do it again. I'll do it more slowly and you'll see how I can do it real quick. Okay, ready? All right, let's look. 6
So,
factorial, 3 factorial, 3 factorial.
Why did you do slash on the 3 factorial and 6 factorial?
Watch this. Okay, I'm gonna break this apart. I'm gonna break this apart. I'm gonna go 6, 5, 4, 3, 2, 1.
Yeah.
Oh, okay.
Okay, and then I remember this down here is 3, 2, 1. But this is that. C'est bon? How cool it looks though?
Yeah, it did look really cool, but.
Thanks.
Now that you're teaching.
All right, not while you're teaching, Grismani. Okay, so that's the first part of it. And in fact, I can write the entire probability function. So the binomial distribution looks like this. That P. All right, so now you tell me what that is.
Yeah, what is?
Use 1 minus p.
I said,
Oh,
oh,
oh, sorry.
I mean, what?
Or probability.
Oh, it's right there.
I know, but that is probability.
Probability of B is Q.
Yeah.
Yeah, probability of A is P. So sometimes when we write probabilities, 1 minus probability will be Q because it just looks like P but flipped over. So it's the corollary to P.
Yeah.
Right? If probability is P, then the inverse of the probability would be Q.
Yeah, well, no, but, yeah,
wait, I know.
yeah, I know that, but it's just like, what are you saying about, because you have 27%, like 26.
Oh, that's why.
Yeah.
Okay, so here's the question. Is it the most likely outcome?
What?
To get 3 heads.
Wait,
No.
actually,
Is it? Oh,
just because it has like 31.5% probability, doesn't mean that's
Let me do it.
optimal probable. We have to do like.
Mine was not any more likely. I think any combination of the 6 points made the same likelihood.
What if you make n
Good question. What if you make any different?
And
Oh, that way you just-
But for the same number of trials, any combination of a 50-50 point of like. Any head, tail, whatever,
Okay.
you want them to be the same probability.
What if we do 10 columns?
Well, the probability of getting a heads or tail in each independent trial is the same. Right? But if I change how many of them I want, the probability either goes up or down dramatically. So if I only want one tails out of 6 trials, is that more or less likely than if I wanted 3 heads out of 6 trials? What's that?
Wait, you only want one head?
If I only want 1 head, is that more likely or less likely than 3?
For any. Or like, if you just want one, you only care about the outcome of one, and not the rest.
I only want 1 total heads.
Oh, and any of them can be.
Any of them can be 6. Oh, sorry, any of the 6 can be heads, but I only want 1. If I get 2, I don't win, right? What's more probable? 3 heads or 1 head?
Okay, let's.
We should use a different equation, because I keep changing the X number and I'm getting the same answer.
I think you know.
How do you change this number and you get the same answer? So this number is here,
You have to like.
Oh, I need to change that number.
yeah,
Uh,
and this, it's numbered here too, right? So if this is p to the 1 versus 6, this is p to the 5,
for sure the P and Q thing is staying the same, but
but this one changes dramatically. So there's how many ways to make it?
There-
There's 20 ways to make 3 heads.
Oh, there's only 6 ways to make one head.
6 ways to make 1 head, and you can just guess that, right? Just go, oh, each one. So probability went down a lot. Okay, so what's the most likely outcome? Three heads, is that true?
Oh, well,
It's both, it's a trick question, it's both 3 heads and 3 tails. That's, shut up, Grismani. Okay, but they're, no, and here's why it's annoying, and here's why it matters, right? What about 4? What about 4 heads? What? 4 out of 6. You tell me. It has to go down, right? Because it's the same as 2 tails. Right? And we already knew that 2 tails was less than 3 heads. So it's very annoying, and these things happen simultaneously. Okay, so when we look at the probability distribution, you'll see that this one was only like 0.3 or something, but that's still the best bet you're gonna get. So the fact that she won it, obviously frustrating to you, right? Okay, good, binomial distribution?
Yeah.
Okay. Can you use it? Okay.
Yeah, well. Are you gonna get that? So, in my project, I'm looking at Binomial, and using this for triple double Poisson ratios. And it's just every time a sample is a case, they put in the frequency data equal to multiplier to.
it's a lot of words to have to explain.
I'm getting there. Okay. A sample is a case. There's 3 systems, and every time that it's a case, it's trying to pick them up, and it's the probability of picking them up.
oh, so you feel like it picks up or it doesn't pick up.
Yeah, and it uses this equation of the event state complaints.
Like also with PNL, when you guys were talking about skew and variance, in my project, like I'm determining like how much like lead isotopes can actually plant themselves into like various materials. And the program can make a histogram of it, and it would actually like give me like a full histogram and tell me like what's its variance, what's its skewness and stuff like that. It's really interesting.
Yeah, those are your four central moments, and you will use them over and over and over until you get sick. I'm gonna skip fast the negative binomial, the geometric and the hypergeometric. You can find these in your book. And I'm gonna go to everyone's favorite distribution of all time. Okay. Of course, we did not get to continuous distribution, but we'll do that, I guess, on Monday. Okay, so the best distribution there is, all time, number one. Number one that Sarah works with, actually, the very first one, is countable random things. This is called the Poisson distribution.
Fish distribution?
The Poisson distribution. Why are you saying fish?
Poisson, French.
It's also a name.
French guy's name. His last name's French. Is he French? Yeah, he is.
That's what Chris is French. The Poisson distribution is not named after a German. Okay, so. The Poisson distribution describes the probability of obtaining a given number of successes, but for which the number of trials cannot be enumerated. Okay? So this describes when things can happen in a continuum. So if I'm talking about dice, right? Finite set of sides. I don't know why I can't grab something. So finite set of sides, and therefore the range is finite. For Poisson distribution, the range can be infinite. But is discrete. Give me an example. What does discrete mean? What does that mean? It only happen in integers. Things can only take whole values. Okay, so what can happen, but only in, what can happen over a continuous range, but only in discrete values? Any personal example? We'll go back to yours in a few seconds, because I know you know. But it's another one.
Or that can go.
Well, technically it can go infinite, but that's not one we're gonna use. Those are quantum mechanicals. Different types of distributions. Talk about your daily life. The possible outcomes, yeah. So when I say range here, I mean values of X that can be chosen. That make sense? Okay. Example.
Maybe like a people example, because you can't like,
You can't
half a person, yeah.
Good, you can't cut, I mean, often you shouldn't cut people in half. So let's give me an example of people, what do you mean?
Like, if it's a concert, like there could be, not an infant, well, I don't know,
There's not infinite number.
Sure,
well. There's a lot.
there's a lot, right? So we could approximate, so how many people show up to the concert? That would be a Poisson distribution. Because some people show up to, no one shows up to that concert, or it sucks. And some are like Taylor Swift and have 90,000 people, right? Okay, so they're all countable, like you said, so that would be very rude to not count a person as a whole person unless they snuck in or something. And so the head count is a Poisson distribution.
Even though it's not like infinity.
Yeah, well, in practice, it should go to infinity. And if there were infinite people, then the Poisson distribution would still be valid. But is it still valid if the sample that you're thinking about has limits?
Can be, doesn't have to be.
Yeah, range can be infinite, but is discrete. You see the difference? Well, because I mean, think about it in the context of how many infinite things there are. Is there infinite energy? No. Are there, you know, if you're going to the example that I always use is the same one. You go to check out at the grocery store. How many people are in front of you? No, not 5.
A number.
A number, a random number, right?
Okay, this can't be,
But there's always a real person, there's not a half person in front of you,
Unless it's
unless it's a child, okay?
well, I don't know, it works this way.
Maybe how many paying customers are in front of you is a better way to say it, right? Because people, you're right, there could be multiple people, maybe there's a baby and they don't contribute to your line, how long your line's taking. Maybe it's an old person, they contribute 7 times as much, right? You don't know. But my point is here is the Poisson distribution is used to describe events that are statistically uncorrelated with one another. That is to say, the influence of one does not create the second one, right? They're independent events. They're discrete. And the range can be infinite. Does that make sense? But it's gotta be countable. So when you hear in math, people talk about countable and uncountable infinities, this is a version of a countable infinity that you will need. Make sense? You guys know which infinity is bigger? All of the real numbers or all of the numbers in between 0 and 1?
You want to say between 0 and 1.
Yeah, you can think about that one. That's a fucked up home problem.
Oh,
It's about how big infinities are, and it's a mathematicians love this shit. I think it's fun, but only for, getting. Okay. So given some mean occurrence rate, we're gonna define it like this. This will be the mean. So for your example of how many people are in front of me at the grocery store, you said 5, right? That would be this value here. And the Poisson distribution P describes the likelihood that exactly X events will occur. So if the mean is 5, and I want to know, am I going to be able to get out really quickly? What is the probability that only one person will be in front of me? Right? That would be the question that I was asking. Okay? Want to see what it looks like? Really pretty. It's n factorial over x factorial of n minus x factorial p x 1 minus p n. Wait, what's that? That's not the Poisson distribution, is it?
Fine.
That's the binomial distribution. Good, okay. So now what I want to do is I want to take n and I want to bring it to infinity. Good money. You asshole. Okay, so what does that do? What is the limit of n going to infinity?
Fine.
Let's do the first part. Let's do this part here.
Oh, wouldn't it just be 1 over x factorial?
Isn't it?
Would it be 1 over x factorial? Because
cancel out.
he did that once.
X could be like arbitrary and small, so technically, if that one's like going to infinity, it's fine, I am just eventually drop off. So it'd be,
Then, yeah, that's not really bigger though, so it'd be like.
Okay, we might need a few more minutes on this. You can think of it in the context of the Stirling approximation. And you can see the relationship there too. But if you say to yourself, okay, this is getting really big and this is getting really big. Okay,
It's getting bigger,
so what?
top will be bigger.
Yeah, so the top will be bigger, so will be a number, won't be 1. Okay. Just write it because we're out of time. Is that okay? Okay. So the limit, it'll be the limit of n going to infinity of n times n minus 1 times n minus 2, so on and so forth, right? All the way down. But if n's really, really big, then that really looks like index. I know, it's pretty. Okay, what about this part? 1 minus b. This has an n in it, right?
Yeah.
Smaller,
What's that?
maybe it's smaller.
Yeah, it's gonna get smaller, right? It's like 1 minus p.
The powers,
What's that?
the powers keep getting bigger and keep negative.
Well, remember what we think about, when we think about the probability of P happening, 1 minus P is all of the things, right? So all of the individual probabilities, as you get more and more things, each individual probability is getting smaller. Right? So P is going down. So in this circumstance, if I want to know what this is going to be the limit as n goes to infinity, and the limit as P goes to 0. Okay. And it'll just be a 1 minus P n minus x, just want to make sure I don't put this on, which is the limit of P going to 0 of 1 minus P over 1 minus P x lambda over P. And remember, lambda was the mean occurrence rate. Right? That was that average value that we're going to assume for all of the pieces. Right? Which sends this to e to the minus lambda 1 as P goes to 0. This becomes 0. This becomes plus 1. Right? And that disgusting thing, that binomial distribution, under these two approximations, becomes the Poisson distribution, which is simply e to the minus lambda, lambda to the x over x squared. Okay. All right, that's long. We can restart this part in more detail, but what you'll notice here is this now allows for the number to be as large as you want it to be. Right? Here's your rate. This can be a very large number. Say x is a very large number. But it's also going to be moderated by the factorial at the bottom. So you're going to get a reason. Make sense? Okay. This is used for Sarah's work. How many things will come out of a piece of radioactively decaying substance? That's the Poisson equation. How many objects will appear in radioactivity? Okay. It also describes how many people will be in front of you at a grocery store. And we'll see that first thing on Monday. Okay, but practice it at home. Calculate for yourself. 5. I want 1 person. 5. I want 1 person. What's the probability? Okay. Break.
I got one. Yeah.
I don't want to be